Let us talk about this problem. We are given a singly linked list. Our task is to segregate even and odd nodes. And we need to keep the relative order of all the even nodes and odd nodes same. For example, if we are given this linked list 17, 15, 8, 12, 5, we need to first put all the even nodes. What are the even nodes here? 8 and 12, right? We put them first. Then we put all the odd nodes. 17, 15 and 5, and their order has to be same. 17 came here first, so 17 should come here first. In this example, we have a corner case where we have all the even nodes, so we maintain the linked list as it is. We don't make any change. Similarly here we have all the odd nodes, so we don't need to make any change in this linked list. Now please pause this video and think of an approach that takes head reference or head pointer of a linked list and modifies the linked list in such a way that all even nodes in the same order appear first and then all the odd nodes appear. Let us first talk about a naive solution to solve the problem. This solution works in theta and time and requires constant auxiliary space. But this solution does two traversals of the linked list. What we do here is, we are given only reference or pointer to the first node. So we traverse the linked list and find the last node reference or pointer. We get hold of this node, right, in the first traversal. Then we traverse the linked list again, and whenever we find an odd node, we insert it after the last node. So if this is our linked list, we'll first get hold of the last node, right? We'll mark it as last after the first traversal. Now we'll traverse the linked list. We see, okay, it's an odd node. So we'll remove it from its current location and we'll insert it after the last node. 17 we'll put here. Now we will traverse 15. It's also an odd node. So we'll insert it after the last node and we'll update the last as well. After inserting, we update the last node as this 17. Then we insert 15. We found 15 as the new last node. And after 15, we update this as the last node. Then we come to 8, it's an even node, so we don't make any change. 12, we don't make any change. 5, we inserted it after the last node. We remove it from here, right? And we insert it. So this is a direct link from here to here now. And we insert 5 here. So this becomes our modified linked list. This is our new last, right? And we need to traverse this till this point, the first position of the last node, right? That also we need to ensure by storing probably last in another variable. So this is how this solution works. It's clearly requiring two traversals of the linked list and it's maintaining extra last pointer or reference. Now please pause this video and think of a solution that works in one traversal, and that's how it becomes an interesting interview question. Let us now talk about the idea for the efficient solution or one traversal solution. So what we do in this solution is we maintain four variables: even start, even end, odd start, odd end. So what we are going to do is, we are going to traverse through the linked list, right? And we are going to maintain two sublists, right? And first sublist is going to be the list which contains all the even nodes, and these sublists are the sublists of our resultant list, right? So the first sublist is going to contain all the even nodes. The second sublist is going to contain all the odd nodes in the same order. So if I begin from here, I see that this is an odd node. So I set odd start and odd end as this node, right? So we traverse the list, the input list, and we update these variables: odd start, odd end, even start, even end. So if the node is odd, then we definitely update odd end, right? We insert the current node after the odd end and we update the odd end. Since this is our first odd node, so we are going to set odd start and odd end both, right? We are going to do like in the even case, if this is our first node, then we'll set even start and even end both. If this is our first odd node, then we'll set both odd start and odd end. So they both are set as 5. Then we come to 10. 10 is our first even node. So both even start and even end will be set as referring to 10 node. And these four variables are initialized as null in C++ or Java and none in Python. So after this, we'll traverse our third node. This is 7. So what we'll do, this is an odd node. So we are going to insert it after odd end. And odd start would not be updated this time, right? Odd start will remain at 5. So we update odd end as this, and we insert the current node first of all after the current odd end, which is this node. After 5 we insert 7 and we update the odd end. This is how we traverse the whole list. Suppose there was one more odd node, then what we would have done, we would have added that, say this was 9, we would have added 9 after 7 and updated the odd end as 9. and there was one more even node, then we would have added that node after 10, right, and updated the even end. After we get this modified list, what are we going to do is we are going to make odd. So our first list should be the first part of the list should be containing all the even nodes. So what we need to do is we need to make even end dot next or arrow next as odd start, right? So we need to write this line even end dot next as, in case you are programming in C++, you will write arrow, right? In other languages you will use dot, as odd start, right? So you will connect all the odd nodes after the even nodes, right? So this is what we are going to do at the end, right? And we'll return our even start as new head of the linked list, right? That's all we need to do. But we need to handle some corner cases. If there are no even nodes, there are no odd nodes, right? That you can write the code and you can take care of these cases. So please pause this video. Now you have complete idea, and write the complete solution that handles all the cases and implements this idea. Let us now talk about C++ implementation of the idea we just discussed. So we have initialized 4 pointer variables: even start, even end, odd start, and odd end, right? Then we run a loop to traverse through the list. And inside the loop, we check if the current node data is even. If it is even, there are 2 cases that arise. If it is the first node, if there was no node in even list before it, then we make even start and even end as the current node. And if there has been nodes before this node, then we insert this node after the current even end. And we make even end as even end arrow next, or we move the even end to current. We could have written even end equal to current as well. That would also work. So what we do, we begin from the linked list after initializing these 4 variables as null, right? And we see this node as an even. We come here, right? We set even start and even end at this node, right? We come here and we set even start and even end as current. Then we don't get inside any other thing because this is if else everywhere. We come here and we move current to the next node 5. And when node is odd, we'll again come inside this condition because this is the first odd node. So we'll set odd start and odd end here. Now we'll come to 4. When we come to 4, we'll come into this else part. We'll insert it after 10. So 10 will connect with 4, right? That's what I've shown here. Then we'll come to 3. We'll come to this else part, odd else part. And we'll connect it after 5, right? So 5 next will become 3. And we'll update odd end here. And we will update even end in the case of 4. Now we'll come to 6. 6 will add after 4 and we'll update even end, right? And after we've traversed the 6, we'll see null and we'll come out of the loop. And now this is the status of our linked list. So what all we need to do? We need to make end of this node as this node. So even end arrow next should become odd start, right? And odd end arrow next should become null. Currently it's going back, so it should become null. So these are the 2 things we have done here. Now this condition is to handle the corner cases. So in corner cases, we have all odd nodes or we have all even nodes. So in both the cases, we'll have either odd start as null if all nodes are even. If all nodes are odd, then we'll have even start as null, right? So in both the cases, we don't need to modify the linked list. If we have 10, 6, 4 all even nodes, we need to return the same list as it is. If we have all odd nodes, say 1, 3, 5, then we need to return. So we return had in this case. So this is the overall solution. What is the time complexity of the solution? This time complexity is clearly theta n. We are traversing through the list once, and it's simply doing one traversal and requires constant auxiliary space.